Okay, good morning. Let's go ahead and get started. What you're seeing up here on the screen is a screenshot of the calendar that you would see on Canvas, or at least this is what I see on Canvas. And so I just want to point out a few things. Again, these are the class meeting numbers, followed by the date, kind of a list of topics that we cover, where in the book you can find the material, and then some highly recommended practice problems. The thing that I want to point out today is that we're moving along here, and one of the things that I said is every 10 days we'll have an exam. And it doesn't show up very well on this projector, maybe, but meeting number 10 is going to be next Wednesday. That's an unfortunate date there. I didn't choose it. We are here today, though, 1 week before. And so what I want to say is if you want to review the materials and say what's going to be covered on the exam, I would go over this list of topics and stop right here. Okay, so the exam coverage will go through day 7. Okay, that's just kind of been my habit over the years. If I have an exam on a particular day, say Wednesday, then I kind of stop the material 1 week before, roughly, and that'll be right about there. Okay, so that would be a good place to kind of stop the material. We're going to continue on Friday with new material, but these topics I won't put on exam 1. Any questions? Okay. So the topic today has to do with this idea of reviewing the Z-transform. First, I want to give a little bit of motivation of why we have to introduce another transform, and then I'm going to introduce and talk a little bit about it and its properties. Okay, for some of us, this will be new. Okay, depending on where you did your earlier work in electrical engineering, and because in our curriculum here, we tried to introduce it in linear systems and signals, 2120. Okay. Some of you may have got it, may have received it, but because I believe it tends to come toward the end of the semester, some of you may not. Then, of course, there's the issue that you may have taken in the spring and all the summer came by, and you empty your mind to make room for new materials, and so you may have forgotten. That's okay. We're going to introduce it or review it today, and so hopefully it'll come back to you. Okay, I want to remind us that we've talked about transforms. Let me just kind of back up a little bit. Recall the rationale, the reason for transforms. Okay, and the primary idea that I say is it's a practical issue in the sense that sometimes if we transform or translate a problem to a new different language, the problem may be easier to deal with in that language. So, for example, we have this idea of the Laplace transform. If we discuss signals in time, we may indicate it using this notation, y of t. If we transform it using the Laplace transform, we use a different notation. We say we're in a different language. We'll call it capital Y, not to confuse it with little y. And we use a new operator called S, not in time. And the advantage in this particular type of transform was that the derivative, as an example, transforms to a multiplication by S. And so this operator, d by dt turns into multiply by S. Technically, I have to take this, but we also remember when we're reviewing for exam 1 that we ignore the initial condition when we're dealing with transfer functions. Now, if we're trying to find the full response of the system, yes, we do need this term, but we're looking at just the response due to inputs. So the rationale was that rather than having to deal with calculus, we deal with algebra. Now, most things that we're going to discuss in this class are about systems whose behaviors exist all the time. They exist continually, okay? Hopefully you're alive and awake continually. The temperature in this room exists continually. And so we'll talk about continuous time. But there are certain things that are discrete time. And so what I want to do is I want to talk about the fact that there are certain things in life that are discrete time. Things with discrete time behavior. Okay. A lot of things. One of the things that can happen is we try to control the world that we're living in, and how often we look at the thing that we're trying to control, and how often we make a correction may occur in discrete time. This happens with a computer. So, for example, maybe we're trying to control a motor. Let me just draw a block and say this is supposed to be a DC motor here, and a DC motor's input is a voltage, and maybe we're interested in the speed of the motor. So this is what's going to happen if you're in ELEC 3040 lab. By the end of the semester, you'll figure out some way to control the speed of this motor. But you're going to do it with a microcontroller, which means that it's inherently a computer, a discrete time device. Parenting a child is increasingly more and more discrete time, to my dismay. You hear our parents, they don't watch their kids except once every hour because they're busy texting, and so the kids are running around. Or you have parents who are just absentee from being a parent, and once a day, once a week, they take a look at their kids. And so sometimes the input to the child is not very often, and sometimes we don't observe what the kid is doing very often. So we have inherently a discrete time behavior. So these are continuous time signals. Voltage exists continually, speed exists continually. What we do in engineered systems, a lot of times what we'll do is we'll put on here something that samples the information. This is what we call a analog to digital converter. I'm just going to abbreviate with ADC. Okay, this converts speed, which if we were to sketch it, maybe the speed in time exists continually like this. But what we do is we sample the information periodically, and so the information only appears in the computer at moments in time like this, which I will draw as little stems. All right, here the horizontal axis is in time, t. Here the horizontal axis here, I'm going to say it may be an integer number, k. So this would be time 0, k equal to 0. This is the first sample, the second sample, the third sample. Here time exists continually. Here in the sample domain world, it only exists periodically. And there's this time period called the sample time. And so this is called t, the sample period. Okay, this is an A to D converter. Those of you who are in 3040 lab, later on this semester, there's an A to D converter inside your microcontroller that you're using, and we'll learn how to use that thing. So basically it takes information that's inherently continuous time and then samples it, and we get only information periodically. Okay, so there's a lot of issues here. The fact that you're sampling means you are potentially losing some information. You are losing some information, and the question is, to what extent is this a faithful reproduction of that? We're not going to cover those issues today. Today I want to just focus on how do we model things that are looking inherently discrete time. On the front end, because we're going to control the motor with a microcontroller, so the output of the microcontroller is inherently a sequence of numbers. Okay, you have this is an input. This is again 0, 1, 2. This is a sample instance. And so these are numbers in my computer algorithm. Okay. Over on this side, when we sample the information, the output, these become pieces of information stored in the computer. And so the feedback control system, basically all this, once we store it and then we process it, all this, this feedback here, this is all going to be in discrete time. It's going to be in discrete time. Okay. So we have here, we have information. We say we want to control the motor. We want to either increase the voltage or maybe decrease the voltage. But these are just numbers, so we've got to convert these numbers to a real voltage. And so there's another box that does this, and we typically call this a digital. This is digital world. This is the analog world. We put a DAC, a digital to analog converter. Okay, so we have two things that have been introduced here. An ADC is an analog to digital converter. And a DAC, a DAC, is a digital to analog converter. Digital to analog converter. Okay. So this is one way we could end up with signals that are discrete in nature. Okay. We may be sampling information from the world. All right. Now, other things are inherently discrete. Another thing that's inherently discrete might be my bank account balance. Okay. Let me call that a bank account balance B, and I'm going to say it exists. I get a number every month for my monthly statement, and so this is the month index. Okay, this is the index for the month. Okay, I'm going to denote things that are in discrete time, or distinguish them from continuous time by using square brackets instead of parentheses. I'm going to use the letter K instead of the letter T. So the bank balance is inherently something that changes monthly, not continually. Okay, notice these are parentheses, whereas these are brackets. So this is one way I could distinguish between the two. Or you might want to say B sub K. This is sometimes a notation that people will use. This is something that increments. K equals 0, 1, 2, 3, so forth, like this. T is continuous. It's a real number. Okay. My bank account balance, I might describe this way. I might say that my balance next month is the same as my balance this month, multiplied by 1 plus R. And R here is the interest rate. Okay. So it says that in the absence of interest, what I get next month is the same as what I got this month. But hopefully I'm saving in an interest-bearing account, and so it's growing by the interest rate. Now in this day and age, the interest rate is not very large. We could further add to this model by saying maybe I have an input to the system, and if I'm frugal, P might be a payment that I put into this might be a payment from income, my paycheck. P stands for paycheck. Hopefully, all of y'all will get one of these soon. Okay. This is not a differential equation. You see no d by dt operators here. This is an example of what we call a difference equation. Okay, this is an example of a difference equation. That's the term we want to review today. Calculus in continuous time differential, d by dt. In discrete time, we have this idea that there's something different the next sample time compared to this present sample time. In this case, it happens to be a scaling 1 plus r, like 1.1, 10% interest. So we call that a difference equation. So we say, well, can we solve difference equations using the Laplace transform? It's kind of kludgy because these aren't really derivatives, okay? And these aren't continuous time signals. And so if you do that, and some textbooks will teach you how to do it, then the math ends up being horrible. So all the advantages of using a Laplace transform will disappear if we try to apply the Laplace transform to difference equations. It's using a tool not for its intended purposes, and so the math gets bad. So what we want to do is we want to introduce this idea of a Z transform. Think of it, Z transform. A Z transform is inherently for discrete or sampled systems. For discrete and for sampled systems. Those of you who are maybe looking for a technical elective before you graduate, you might say, I want to take the Dr. Reeves Digital Signal Processing course, DSP. DSP is happening now. This little recorder is recording my voice. It's supposed to be existing continuous time, but it's being sampled. That's like one of the examples. Everybody's got a cell phone with a couple cameras on it. That's sampling the colors and the light intensity that exist continually in time in the world, but then reproduce it on an array of color intensities. And so those are all, again, sampling the world, and because it's in pixels, it's also discrete in nature. Not discrete in time, but discrete in space, but it's still discrete. And so if you took the course Digital Signal Processing, he's going to introduce this idea again for the Z transform. Okay, don't tell him that I introduced it to you, because then he'll say, you didn't do a very good job, Dr. Hang. You'll just say, thank you, Dr. Reeves, for introducing to me the Z transform, but you'll see it again in DSP. Okay, so let me tell you what is the Z transform. Fortunately, the Z transform for discrete time systems is much easier to define than the Laplace transform. You may remember the Laplace transform involved an integral. It was awful to work with, but it was a necessary part of transforming continuous time signals to S domain. All right, so if I have a sequence, of numbers in time or in samples. I'm going to call it, these are square brackets. These are supposed to be square brackets. Y of 0, Y of 1, Y of 2, Y of 3, like this. And let's suppose the numbers are 7, pi, E, 9. Okay? These are just numbers. A bunch of real numbers. Some are irrational, but they're just a bunch of numbers. These are their values, okay? Then the Z transform, I'm going to write it in shorthand notation, is you take each of the numbers, y of k, and multiply it by z to the minus k. Take each number and multiply by z to the minus k. And you do that for each of the numbers, and then you add up all the terms, k going from 0 to infinity. So this is the math definition of the Z transform, of a sequence. And so for this example, we would say the Z transform is, let's just take the first number, 7 times z to the 0. Z to the 0 is just 1. The next term is, I have to add, see that's a sum. The next term is y1, which is this, pi, and I multiply it by z to the minus 1. And then the next term I have to add, see the sum, is going to be e, the number e, that 2.71828, blah, 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 so on and so forth, times z to the minus 2. It's the second number in the sequence. And then the next number in the sequence is this last one. It's y of 3. And y of 3, I would say it's this number multiplied z to the minus 3. So this was the sequence of numbers in k. Okay. This was k equal to 0, 1, 2, 3. These were the y of k's. Okay. And this here is the z transform of that sequence. Okay. So that's the basic definition. And then if I wanted to recover the original sequence, if it's written out explicitly in this form, then what we can do is we can just say, okay, this is y of 2. This is y of 3. This is y of 0. Okay, this was their actual values. Now, one of the properties of the z transform, which is useful, one of the properties of the z transform that is useful is what we call the shift property. Okay, so if I have y of k, a sequence of numbers, k going from 0, 1, so forth, 0, 1, 2, 3, dot, 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 and I do a z transform, then I'm going to call that new animal capital Y, just like I did in Laplace transform. This was in time, little y. This is in the new language, capital Y. It's still the same thing. This is speed, but this is discrete sequence of numbers. This is going to be the transform of those numbers. This is indicating sample indices. Okay. This is some operator, z. Okay, so the notation is going to be called y of z. Well, shifting means, let's suppose I take a look at that information shifted in time. This is also an integer. I shift it back in time. Then, if I do this, the z transform is simply taking y of z, the original sequence, the original transform, and then multiplying by z to the minus n. And if I shift it forward, this is a backward shift, delay it. If I shift it forward, n could be for example, a negative number here. Then it's shifting forward in time. This becomes a positive. Okay. So, as an example, let me do again 2 sequences. K equal to 0, 1, 2, 3. Just let's do a short sequence like that. And let's suppose y of k is equal to 4, 9, 7, 5. Okay? These are the values. Then here, y of z is going to be equal to 4 plus 9 z to the minus 1 plus 7 z to the minus 2 plus 5 z to the minus 3. Okay, now let's suppose I have a new sequence. I'm going to call it P of k. Okay. And the difference is that P of k here is going to be 0, 4, 9, 7, 5. Okay. Then P of z
is going to be 4z to the minus 1 plus 9z to the minus 2.
Just applying the definition now.
Plus 7z to the minus 3 plus 5z to the minus 4.
You know, if I look at these two, I say these are very similar. The only difference is it looks like I've taken this sequence and multiplied everything by z to the minus 1.
Okay, this is, in other words, this is just simply equal to the original sequence, y of z multiplied by z to the minus 1. And so what that tells me is that p of k is just y k minus 1.
It's just taking the same information, y of k, 4975, delaying it one sample, shifting it in time one sample. Okay, everything just shifts over one sample. And so these are the respective transforms. So let me go back to the example of the bank account. Bank balance. What I might say my bank balance today was the same as my bank balance last month. This is another way to model bank balance last month, multiplied by 1.1. 10% interest. Nice. Unheard of, right? Actually, my lifetime, there was a time when you could get 10% interest on a bank account. What would you do if I told you you could get a bank account would offer you a savings rate of 10%? What would you do?
I'll take it. Assume the economy is up.
Would you start saving? 10%? Double your money in how many years? 7.2. There's a thing called the Law of 72. Google that right now, the Law of 72. It says that if you save at a rate of 1%, compounded annually, it takes 72 years to double your money. If you save at 2%, it takes 36 years. 10%, okay, so it's 72. Okay, Law of 72. Compounding, assuming you're doing compound interest. Okay. So you would save, right? Well, I'll tell you, there was a period of time when the interest was like that. But the problem was the mortgage rates on houses was like around 15%. So go home, ask your mom or dad, what is the mortgage rate on their house right now? It's pretty low. We're at historic lows right now. We're at probably, if you search around a little, maybe if you got VA benefits, you can probably get an interest rate 4% or lower. But the savings rate right now offered by banks is really low. So you just can't win, can you? Okay, so this is a difference equation. Maybe we have also a payment. Let's call it P of K. Okay. So in Z transform, I would say this becomes B, capital B of Z. I transform this, call it B of Z. And this is 1.1 Z to the minus 1 B of Z. And this becomes capital P of Z. Whatever my payment is, that's another sequence of numbers. I don't know what my payment is into my bank account. And then now we can do algebra, just like we do Laplace transform algebra, except now we do algebras in Z. And so we can do Z algebra.
We can perform algebra work in Z.
So for example, I could take all the terms involving B and move it over together,
And what I get over here is I get 1 minus z to the minus 1. Oh, I'm sorry, there's a 1.1 that should be squeezed in there. 1 minus 1.1 z to the minus 1 times b of z is equal to p of z. And so I can then write, say, my bank, the transfer function between payment in and my balance, I could express as a transfer function. It's a z transfer function describing my bank balance, the output, relationship to my payment, the input. In this case, is going to be 1 over 1 minus 1.1 z to the minus 1. It's this expression here as a z transform expression. So you go home and your dad says, "Dear, what are you learning at Auburn? I'm paying that good tuition money." And you show him this, and he'll say, "What in the world is that?" And you say, "Well, Dad, that's a Z transform. It describes your bank balance." And you say, "I don't understand that at all. I know what a bank balance is. It's a sheet of paper that the bank sends me every month." He gets that in time. It's a sample data piece of information. You compactly kind of describe it using a language that you as a medical engineer understand. Okay. It will have some advantages with the tools that you can learn to apply that. So it's just another language. I'm telling you, this is just describing the bank balance. This is difference equations. This is a transform equation. Okay, so let me kind of summarize what we've done today. Maybe we'll do it by coming back to this table. Just to kind of review, exam 1 next week. Make yourself a sheet of notes. I strongly recommend that you handwrite your sheet of notes because if you handwrite your sheet of notes, you develop some muscle memory, and muscle memory is a way of learning. Okay? This is why we go to baseball practice. Muscle memory. Muscle memory. Okay? Muscle memory works with learning things at school. So make yourself a sheet of notes. I always get the question, can I use both sides? Yeah. You can use both sides. I've discovered over the years that those who really know the material don't need the sheet, and those who don't know the material won't be helped if I give them 10 sheets. So this is more of a psychological crutch. But go ahead and make yourself a sheet of notes. I would recommend you look over some of the old exams. You should, however, compare the content on those old exams with the content that is, we've covered over the last essentially 7 meetings. There may be some problems. Hopefully you'll recognize when you see a problem and say, wait a minute, we haven't covered that yet. Okay, you might see something like that. You might look at an old exam and say, he didn't have any Z transforms, but I'm telling you, right now, Z transforms will be on the exam. Okay. So the exam 1 is going to cover, again, it's every 10 days, but the material coverage will be, it'll kind of stop 1 week before the exam. So we're going to go through meeting 7, look over this material, look over some of the homework, look over some of the old exams. Today's coverage was basically reviewing or introducing for some of us this concept of the Z transform. And the thing that's useful to us is to understand what happens if I shift my information, delay it by time or advance it in time. It's just simply multiplying by a power z to the minus n. So there's a z to the minus n idea here. And then there's this concept of a difference equation. All right? Friday, we're going to continue on. We're going to take the Z transform background, just this introduction to this mathematical background, and we're going to see how can I take models that I've already been producing in Laplace domain and come up with approximations in Z domain. And that's another practical thing, because most of the time when a person has had some control systems education or control systems background,
They learn continuous time concepts. They understand S-domain models, okay? And then all of a sudden you're saying, well, we gotta work in discrete time because we're working with a digital controller, or we're working with a problem that's inherently discrete. And somebody's saying, but I got all this work that I did in Laplace transform. Are you telling me I gotta start all over? Fortunately, you can say, no, you don't have to start completely over. I can give you an approximation in Z. And so I'll talk about that on Friday. How do I approximate these S-domain models with Z? And there's a lot of different approximations. Approximations are not perfect, you need to understand that. But we're going to talk a little bit about that. So that's why we needed to introduce today this concept of a Z transform. Friday, what I'd like to do is meet back in lab. Go back to the computer lab. We'll do some of these approximations using MATLAB because it's, you're going to tell you about it. Yeah, you don't have to start all over. I'm going to give you an approximation, but it's going to cost you because it's not a trivial matter, and having MATLAB in your toolbox to do it will be helpful. So I'll show you how we can do it in MATLAB. All right, any questions? My watch says